All right, so in this video, I'm going to go over orbital diagrams or orbital notation and also noble gas configurations, or I might make a separate video for that. Okay, so orbital diagrams are basically another way to show electron configuration. So we should start with the complete electron configuration of aluminum first, and then I'll show you how to translate that into orbital diagrams. Okay, so aluminum is in the third period. In the third period, see, there's aluminum. In the P block, that's the location of aluminum. So 3P is the end point of aluminum. That's where we stop. So if we're stopping at 3P, we have to start right here and go back to front on the arrows. So we have 1s, 2s, 2p, 3s, and then 3p. Okay, now I have 13 electrons in aluminum, so I'm going to distribute them 2 to 1s, 2 to 2s, 6, then 2. That makes it 12. So I have 1 left over to put in the 3p1 orbital. Now, here is what orbital diagrams or orbital notation look like. All you do is you are going to look at the letter for each orbital and you are going to draw a number of boxes to represent that orbital. And the number of boxes is dependent on what we drew here. Every S you draw one box, every P you draw three, every D you draw five, and every F you draw seven. Okay, so here is one to represent the 1s orbital. Here's another box to represent the 2s orbital. Then here is three boxes to represent the 2p orbital. Then 3s is going to be another one box, and 3p is going to be three boxes. The letter is what decides the number of boxes. So this is 1s, 2s, 2p, 3s, and then 3p. Now, we have to fill these boxes with electrons. But before we do that, we have to look at the last two rules. We did Aufbau already, but we have to look at the two rules that come after Aufbau. So on the PowerPoint, the three rules were Aufbau's principle. We did that one already. That's the diagonal arrows, 1s, 2s, 2p, that's that. Now we're going to look at Hund's and Pauli exclusion principle. Those are the two that apply when we are filling in arrows or electrons in this situation, okay? So Pauli exclusion principle, which is the second one, says that each orbital or each box can hold a max of 2 electrons, but those 2 electrons have to actually be pointing in opposite directions. And the opposite directions is a way that we show the opposite spin that electrons have. So electrons are negatively charged, right? They're negatively charged particles. So if they want to hang out next to each other, they really don't like it, okay? They hate hanging out next to each other because of the fact that they're both negatively charged. Negatively charged particles will repel each other. So in order to not repel each other, what happens is one of them will turn clockwise and the other one will be counterclockwise. Okay, so the way that we show these counterclockwise and clockwise directions is by drawing electrons, one pointing up, one pointing down. I like to use half arrows. You can use full arrows, it's up to you. But inside a box, no two electrons can point in the same direction. That's wrong. When you're putting in electrons into a box, you have to do them up and down. Okay? Then the next rule is called Hund's rule. And Hund's rule says that when you are within a sublevel, that means like 1s, 2s, 2p, this is a sublevel. Okay? Each of these is a sublevel. When you are within a sublevel, when you are placing electrons, you have to place them unpaired first and then you pair them. So you have three boxes. You have three boxes. And if I'm putting in electrons, if I have to put in 4 electrons, instead of doing this, where you're clustering them all into the 2 rooms, if you have a spare room, you should spread them out like that and only pair them if absolutely necessary. Okay, it's like sharing an apartment with someone. If there are four people in the apartment, if there are three bedrooms, three people can have like the well, only one room needs to be shared, but the other two rooms can just have one person each, right? Why would you leave a room empty where two people are sharing bedrooms while a third room lies empty? If you have space, you got to spread out, especially because electrons don't like each other. So they need to spread out if they have the space to spread out. Okay, so you pair them only when absolutely necessary. You spread them out, so you do unpaired and then pair them. Okay, so let's go back to our drawing and fill in electrons. 1s has two electrons. We got to do one up, one down, and then we go to 2s. You have to fill in each sublevel before you move on to the next. Okay, so 2s has 2, then 2p has 6. Just to practice, I do unpaired first and then I pair them. 2p6. Then 3s has 2, and then look, 3p only has 1. But instead of drawing one box, we have to draw the three boxes available for the p orbital, because you have to show that two of them are empty. Okay, there's one occupied by one electron and the other two are actually empty. So that is what an orbital diagram looks like for aluminum. Okay, now let's do one for phosphorus as well real quick. Phosphorus's electron configuration. Phosphorus ends in third period p block as well. So 3p, okay? So phosphorus will be 1s, 2s, 2p, 3s, 3p. And phosphorus has 15 electrons, so 2, 2, 6, 2. The last one gets 3. 1s is one box, 2s is one box, 2p is three boxes, 3s is one box, and then 3p is three boxes. Your boxes have to be labeled. Without labels, they're just like randomly floating boxes, so make sure to label them. 2 electrons in 1s, 2 electrons in 2s, 6 in 2p, 1, 2, 3, 4, 5, 6, 2 in 3s, and then 3p has 1, 2, 3. Hund's rule says you have to spread them out. So don't put 2 electrons in one box. Spread the 3 into the 3 rooms. If you have space, spread it out, okay? Spread out the electrons because they repel each other. They need to occupy the maximum space possible. All right, so that's how you do orbital notation. I will do a second video for noble gas configuration.